Alrighty, just making sure that audio works. Looks like it does. And now just making sure that PowerPoint's working. It looks like it is. Perfect. Okay, so here is our first section in Unit 9, circles. Okay. And of course, right, our new first says talk about your spring break. Copy those notes down, right? My spring break was pretty good. Did a lot of relaxing, had some fun with friends. Celebrated actually two of my friends' birthdays. That's pretty fun. But I digress. Here is the first key point. Okay, a couple things that I told my classes is that I'm going to do my best to keep all of the fill in the blank parts of a key pointer theorem as one color, so that it's easy to distinguish, and then have something like on the left side with this blue stuff, have that be there for words that we may not know or something like that. That's kind of the idea that I'm going to go with. But you'll see immediately that I actually kind of changed that up, like pretty much immediately. Okay, so you'll see what I mean. But here are the notes. Equidistant. To break down that word, equi means equal, distant means distant. So equidistant means equal distance. Then we have the center point, which is called, well, the center. And then we have the notation that we use. We have circle P. Okay. It all works the same. Here is where I was saying that we were immediately going to change that, but it is with good reason, right? We have a radius, chord, and diameter, and that corresponds to our radius, chord, diameter on the right-hand side with the colors. Okay, so that's the only reason why I have it like that. This word C-H-O-R-D is pronounced chord, not chord. It's pronounced chord. Okay. To make sure this is correct. Radius, I'm sure we are familiar with. It is the endpoint of the center of the point, or center of the circle, and any point on the circle. That's what we call the radius. A chord is a segment whose endpoints are on the circle. Then the diameter is a chord that contains the center of the circle. Okay. Then we go with the next couple. Secant is a line that intersects a circle in 2 points. Okay, intersects 2 points of the circle. Tangent is similar, but it only intersects at exactly 1 point. And that 1 point is called the point of tangency. And you can see all that stuff right there on the board here. Okay, so you can follow along with what I'm saying. Okay. All right. Then we have a turning talk. Are all chords diameters and all diameters chords? And you would say no, then yes. Okay. Yes, all diameters are chords, but not all chords are diameters. Okay, that is definitely an important thing to remember. It's kind of similar to what we talked about in Unit 7, where we said every square is a rectangle, but not every rectangle is a square necessarily. Okay, kind of that same mentality. But then we have example 1 here. Tell whether the line, ray, or segment is best described as a radius, chord, diameter, secant, or tangent of circle C. And so we look at these parts here. And you know what? I think it might be good to kind of highlight for you as I'm speaking. So we have AC, which is this line right here. AC is going to be our radius. And we know it's going to be our radius because we have an endpoint at A on the circle, and we have this center C in one segment. Therefore, it's the radius. Then we have B. AB, segment AB, is going to be this segment where we have A as one endpoint, then B as another endpoint, and it goes through the center. Therefore, we're going to call this the diameter. Okay. Then we have C. C is DE, but it's ray DE. So we start at D as our ray, and then go to E. Well, if DE is our ray, we have this intersection point at B, but we only have exactly one intersection point. This is going to be our tangent line. Something to know about tangent lines, though, is that tangent lines will be on the outside of a circle. Okay, it will never be inside the circle. You'll only see tangents on the outside of circles. Okay. Then last but not least, we have part D, which part D is the line AE. So we start on this endpoint. Let me write it out, but start at that end, go to this end. And this is where you want to be careful. Okay. It intersects at two different places. But if we remember from our definitions, a diameter has two intersections of the circle, and they still happen to be endpoints. A chord has two intersections of a circle, and that so happens to be endpoints as well. And then a secants are usually lines that do not necessarily have endpoints at the edge of a circle. So here we decipher. Well, if secant said line in the definition, it might make more sense here. But it may make even more sense to say that since a chord and a diameter must have endpoints, therefore they cannot be a line. So because chord and diameter cannot be a line, then we can then say this must be a secant. Okay. Make sure you make the distinction. Chords, diameters, and secants are very similar. However, a diameter is a chord. Diameters and chords must have endpoints, and a secant is not necessarily going to have an endpoint. Okay. So if we were looking at AG, for example, AG as two endpoints would be a chord because, well, it's a segment, right? And because those two endpoints are on the circle, therefore it's going to be a chord. But say if we're looking at AE, segment AE, that is also still secant because the endpoint is not on the circle. Okay. Or if we had, for instance, ray AE, where ray AE, A is the endpoint, E is the line going infinitely, then that is still a secant. Okay. Make sure you make those distinctions. Give you some time here. Go ahead and do those problems on your own first. Come back. All right, now that you've tried it on your own first, let's look at PR. Segment PR is this segment right here, and that's definitely our diameter. Okay, that one's pretty easy. Then we have MN, but it is line MN. But it doesn't really matter. We don't necessarily need it to be a line. It could have been a segment, and it would still be the same answer. We only have one point of intersection, and that is the point of tangency. Therefore, we have a tangent line. Very easy, very nice. Next, we have PQ. PQ is a line, and it is this line. So just like how we talked about it in the previous example, this must be a secant because it is a line and it has 2 points of intersection. And last but not least, we have QO, which is just a segment QO, and this is going to be our radius. Okay. Something to realize here is that we always want to make the most specific identification. So although diameter is a chord, you don't want to say chord for PR because there's something more specific about PR. So say diameter rather than chord. Okay. Our next key point, our second to last key point here, where we talk about two kinds of different circle, I guess, relationships, you can say. Okay. But here we have three kinds. Okay, these are all going to be coplanar circles, but any circle that intersects, or any circles that intersect at one point, is what we call tangent circles, which we'll talk about. And any coplanar circles that have a common center is called concentric circles. Again, we'll talk about it. But for the left-hand side with the blue circles here, we have 2 points of intersection. The way that I think is best to memorize this by is think about it like a Venn diagram, where we have, those two circles where you have one thing on the left-hand side, one thing on the right-hand side, and everything in the middle that it has in common. So think about it like that. Then for 1 point of intersection, notice that the tangent circles can be inside and outside, so it's possible, but still look at that line of tangency. That is only on the outside of the circles. Nowhere is it in the inside, except for specifically that 1 point. That's it. Okay. And you'll see on the right-hand side with the green circles that we have no points of intersection. Yeah, I'm going to talk about the left two circles, the ones that are definitely not inside of each other, where we have these two circles here. These are going to be just regular circles that do not intersect. Nothing super cool about them or specific about them. They just don't intersect. However, a circle like this one on the right-hand side, which is this one right here, okay, this one is what we call concentric because they share the exact same center. Okay, notice that this is the exact center. Okay, that red dot there. Well, I want us to think about it like this. What if we have a circle like so? You know what? That's actually not a bad circle, if I do say so myself. But then we have a circle like this. Would that be concentric? Would that be point of intersection with one? So tangent circle, would it be 2 points? Kind of have you decide for that real quick and then come back and we should definitely say that no, this is definitely neither of those, right? It definitely doesn't have any intersection points. Therefore, we must say that there is no intersection points. No intersection. Well, we know it's not concentric because no common center. Okay. So make sure that you know these distinctions. Okay. You can kind of blitz through some of these examples here, and I would definitely take a pause here, look at your problems here, do these 6. They should be really quick, less than 15 seconds. Really should take really 5, but that's just me. But let's go ahead and look at this. How many points of intersection are there in the circles below? And that's for both of these. Here, this first one, we have 0. Second one, we have 1. Third one, we have not 2, sorry. Not 3 either. 2. A, we have none. B, we have 1. And C, we have none again. Okay. Like I said, very easy, should have been pretty good. Okay. But something I want us to write about these two is that there is another way we can use tangent as an adjective, and the word is tangential. Okay, use the word tangential for the problem here. Okay, tangent. So the way you would write it or say it in a sentence is, let's say that this was circle X and circle Y. Circle X is tangential with circle Y. Or if we had a line of tangency, let's call this L. Line L is tangential with circle X and circle Y. Okay, it's just easier to say it like that. Okay, it'll work for both ways. Okay. Here's a bunch of stuff that you should write down in your notes. Definitely the red and blue. Something to look about these theorems, though, is that both theorems are talking about arctangent. So definitely star, circle, box, whatever you got to do to make kind of I guess the word would be to make tangent stand out. Okay, make sure that you know this is about tangents. And basically, theorem 10.1 says that tangent lines are perpendicular with the radius from the center at the point of tangency. Okay. So what this is basically saying is that QP in 10.1 creates a 90-degree angle with the tangent line using point P as its intersection. Okay. So that is the first thing. Definitely something that you should memorize. But you're definitely going to see this later on. And in fact, 10.1 builds into 10.2. You cannot have 10.2 without 10.1. 10.2 says if two tangent lines are the same exterior point, then both tangent segments are congruent. Okay, at first that might not sound like super important. Okay, but there is something that I missed here, right? We should have some congruent signs here. But what this is saying is that the right angle created, then we get a segment that is created. And then look here, PS, that's actually reflexive. So really we have two sides and an angle, but we have a right triangle, so it's actually HL. HL allows us to say that these two triangles are congruent, and that's actually a pretty good thing to know. Okay, it's actually something I didn't say in my previous classes. So it's good to know. But the main thing I want you to get here is this star. If tangent, a right triangle is created. Okay. And so this right triangle, where I'm getting this right triangle from, is actually from creating it right here. We already knew RS existed. That's fine. We know that PR exists. That's our radius. But the part that I actually changed a little bit, and not really even changed, I just connected two dots because you technically could do that. PS right here. Well, if I have those two legs, and I have PS, which is my hypotenuse, it's across from the 90-degree angle, I have a right triangle. And because I have a right triangle, I can use Pythagorean theorem to prove that these right triangles exist. And we'll see that exactly in our next problem. So look here. Is segment ST tangent to circle P? Okay, well, if it is tangent, then that means that Pythagorean theorem is going to work. So we go ahead and we use Pythagorean theorem. I'm going to write it in words first because I think it's helpful to do it that way. So T is our point of tangency, abbreviated as POT, point of tangency. And because it is our point of tangency, that is where our 90-degree angle lives. Well, across the way, that is our hypotenuse. So we're going to write it in words first. And we know this is hypotenuse because 37 is the greatest number out of those two numbers. So SP squared equals ST squared plus TP squared. Well, I already know all these values. I'm just going to plug them right in. 37 squared equals 35 squared plus 12 squared. Well, 37 squared is 1369. 35 squared is 1225. And 12 squared is 144. Add everything on the right-hand side. You get 369 equals 1369. Okay. And so, because we know that they're equal to each other, we just showed it. Our first conclusion should be right triangle exists. But then our second conclusion from there should be ST is tangent with circle P. Okay. So basically, to break this down, if the right triangle works, if Pythagorean theorem works, then you can confirm that ST is tangent to circle P. That is what you can confirm. Okay. But if it does not work, then the right triangle does not exist. Therefore, ST is not tangent to circle P. So next, move on. Try this problem on your own first. Come back. Okay, now you're back. We'll see this problem next. The exact same approach is going to be followed here. T is our POT, our point of tangency, with the right angle, and across the way is our hypotenuse. So write this in words first. SP squared equals ST squared plus TP squared. Okay, notice again the exact same setup, just with different numbers now. SP is 51 squared equals ST, which is 44 squared, plus 24 squared, which was TP. So you plug this into a calculator, we get 2601 equals 1936 plus 576. You add them up, we get 2601 supposed to equal 2512, and they are not equal to each other. Because they are not equal to each other, right triangle does not exist. Then the next conclusion we should say is ST is not tangent with circle P. Okay, very good. Okay. Then, last two examples here. You want to be careful here with example 4. I don't think we'll see a whole lot of these kinds of problems, but you definitely want to be careful here. Okay, those are good. In the diagram, point B is the point of tangency. Definitely should label that. Okay, point of tangency. Find the radius R of circle C. And the radius is in red here. That's what we're looking for. Okay, right there. But I know a lot of us are going to look at this and be like, I have no clue how to find that. How do I do that? Okay, you're going to see those two R's. You're going to be thinking like, oh, I'm supposed to add them or something. And I don't know. Okay, I just know that. I know it's going to happen. Okay, so what we're going to do, we're going to follow the approach that we've been following. Okay, so follow with me. Well, if we know that point B is the point of tangency, we know that there's a right triangle here. Well, across the way, AC is going to be our hypotenuse. So let's go ahead and write this in words first. AC squared equals our other two sides, which is AB squared plus BC squared. So we'll replace with what we know. AB is going to be A feet squared plus BC, which is R. We don't know what R is quite yet. We're looking for that. But then we say, well, you know, AC, is it 50 minus R? Is it 50 times R? 50 divided by R, 50 plus R? You know, it's hard to tell. But it's actually not as hard as we think. Okay. Hear me out. Okay, let's say that this intersection point right here, let's call that X. Well, if I know that AX equals 50, and I know that XC equals R, then if I try to find AC, which is the entire segment, AC by the segment addition postulate way back, I think this actually it was the very first key point and theorem that we actually learned. I think it was like 1.1. AC is going to equal AX plus XC. Well, then AC must equal 50 plus R. Okay, the reason why I put this is because I know for a fact that people are going to write 50 plus R and put it into the square where we have Pythagorean theorem, and you're either going to put 50 squared plus R, you're going to put 50 plus R squared, or you're going to put 50 squared plus R squared. And these are all wrong. You cannot do this. This is not correct math. You cannot do that. What you must do is this. 50 plus R, that entire quantity is then squared. Okay, you must do it this way. It is not going to work any other way. So from here, we just simplify. 80 squared is 6,400 plus r squared. And here for our 50 plus r, if 50 plus r quantity squared is the case, then we have 50 plus r times 50 plus r. And here you're going to use your FOIL method or your box method, whichever one you prefer. I prefer FOIL, so I'll show FOIL. 2,500 for our first, 50r for our outer, r times 50, which is 50r for our inner, and then our last r times r is r squared. So I'm going to combine everything in there before I put it in. I get 2,500 plus 100r plus r squared equal to 6,400 plus r squared. And here, well, I want to get all the r's on one side. Let's go ahead and move everything from the right-hand side, or from the right, sorry, the left-hand side that's not r to the right-hand side. So I'm going to take this r on the right-hand side, and I'm going to move it to, well, the left-hand side. So I'm going to subtract r squared. And would you look at that? It's going to cancel on the right-hand side and cancel on their left-hand side because they're the exact same value. They both equal to 0. So r squared doesn't exist here. Then I'm going to take 2,500 and move it from the left-hand side, put it to the right-hand side. Just like so. And what I'm left with, this is 100r equals 3,900. Because 64 minus 25 is 39, and add my zeros at the end. Last but not least, I'm going to divide by 100, divide by 100, r, right, because those two cancels, r equals 39. And that is our correct answer. And the way you would check this is plugging it right back into r. Okay, so if you wanted to check this, you would put 50 plus 39 squared equals 80 squared plus 39 squared, which of course you don't need to do 50 plus 39 quantity squared. You can just add them because they're now numbers. 89 squared equals 80 squared plus 39 squared. Okay, and that's how you would check it. Okay, long, strenuous process, a lot of time to explain it, but I think it is good to explain it this way. Okay. And here is the final problem. Oh, thank goodness, right? Final problem. But it's pretty much the same thing as the last one, where we have S is the point of tangency, which means we have our right angle here, which means that the opposite side is our hypotenuse. Okay, we're still finding the radius. So let's go ahead and put this into words first. TQ is our hypotenuse, so TQ squared, equals TS squared plus SQ squared, because those are our legs. TQ, same approach to the last problem. We're going to take 10 plus R squared equals TS is 20 plus SQ, which was R squared. And you're going to do your FOIL method, but it's actually pretty easy. And I am actually simplifying it. 20 squared is 400 plus R squared. Do the exact same approach. Oops, I don't know why I put an equal sign right there. Then we subtract R squareds. They cancel on both sides. Subtract the 100 on one side. You have 20R equals 300. Divide by 20. Divide by 20. R equals what? 50. Yep, 50. Very good. Again, if you wanted to check this, 25 squared, realize I put 10 plus 15 to equal 25 squared equals 20 squared plus 15 squared. Okay, that's how you check your work. All right. Well, I hope you had a good spring break, and this is our first lesson back. Well, glad that we have started our first lesson pretty good, but other than that, I think we're pretty much done here. If I can stop sharing, here we go. I don't know why it's not doing the thing I want it to do. Oh, that's why. Yeah. And now it should be good to go. All right. I'll talk to y'all later. Bye-bye.